Welcome back to our Software Engineering Explainer. Today we're diving into section 5.4 of your textbook, Behavioral Models. We're actually making a really exciting shift today. We're moving our focus away from the static architecture of a system, and we're going to look closely at its dynamic execution. Think of it like looking at a building. Previously we looked at the floor plans, but today we're going to look at how people actually move through that building and interact with it.
Here's our roadmap for today's session. We're going to start by comparing structural and behavioral models, then we'll break down data-driven and event-driven modeling. After that, we'll see how superstates help us manage complex systems, and finally, we'll wrap up with a laser-focused exam review. Let's get right into it.
All right, Section 1, Structural versus Behavioral Models.
So up until now, we focused heavily on structural models. Think of those as your static blueprint, the basic organization and architecture of a system, like the classes and their relationships. But behavioral models, they are all about the timeline and the logic. They show us what actually happens dynamically when the system runs and responds to its environment. It's the system in motion.
Now, to get a system to actually do something, it needs a nudge from its environment, right? We call that nudge a stimulus. And these stimuli basically come in two flavors. First up, we have data-driven stimuli. This is where the sheer arrival of data triggers the processing, like a phone billing system that kicks into gear the moment it gets a massive batch of call logs. Second, we have event-driven stimuli. This is when a specific physical or software event happens. Think of a landline switchboard reacting the exact second you pick up the handset. It might carry data with it, but it's the event itself that triggers the action.
Moving on to Section 2, let's take a closer look at data-driven system modeling. So, what exactly is data-driven modeling? Well, it's a way to map out the complete end-to-end sequence of actions involved in taking input data, crunching it, and spitting out an associated output. These models are an absolute game-changer during requirements analysis because they let us track the entire journey of a piece of data as it travels through the system.
Let's make this concrete with the textbook's insulin pump example. We map this out sequentially. Step 1, the system gets a sensor value. Step 2, it uses that value to compute the patient's blood sugar level. Step 3, it calculates the exact insulin delivery needed. And finally, Step 4, it sends commands to actually control the pump. Back in the day, we used data flow diagrams, or DFDs, to show these steps. But today, we generally map this end-to-end flow using UML activity diagrams, using rounded rectangles to represent each computational step.
Now, here's a little pro tip you should definitely keep in mind for your exams. Different people like looking at systems in different ways. Stakeholders and non-programmers, they usually love data flow and activity diagrams because they clearly highlight the operations, the what is happening. But software engineers often prefer UML sequence diagrams. Why? Because sequence diagrams highlight the specific objects in the system and precisely how data passes between them over time.
This visual brilliantly captures a UML sequence diagram in action. You read these from left to right, watching the data flow sequentially. See how a purchase officer fills in an order, then the order object validates it. If it passes, it checks the budget, updates the amount, saves it to the order's data store, and eventually sends it to the supplier. It is literally a timeline of messages passing between objects to get a job done.
Okay, Section 3, Event-Driven System Modeling.
All right, let's switch gears. Unlike data-driven systems that are just happily churning through data pipelines, event-driven modeling is built on a different assumption, that our system has a finite number of distinct states, and an event, or a stimulus, is the spark that forces the system to transition from one state to the next. For example, a software-controlled valve moving from an open state to a closed state. This approach is absolutely critical when you're designing real-time control systems.
The textbook has a really fantastic, relatable example for this, a standard microwave oven. We map this using a UML state diagram, where our finite states are the rounded rectangles. So the microwave just sits there in a waiting state. You press a button, boom, that's an event, and it transitions to the set time state. You close the door, another event, moving it to the enabled state. Finally, you hit start, and it jumps into the operation state. It's stepping from state to state, based entirely on specific triggers.
But here's the thing, while these state diagrams give us a gorgeous visual overview, they don't hold all the gritty details a programmer needs. That's why we always back them up with a detailed table like this one. Look at how it explicitly defines what each state actually means. Waiting literally means the oven is waiting for input and the display shows the time. Half power specifically means setting the generator to 300 watts.
Documenting this removes any guesswork for the team writing the actual program code.
And of course, we do the exact same thing for the stimuli. We rigorously document the triggers. Full power means the user pressed the full power button. Door open means the physical door switch is no longer closed. By tabulating the whole shebang, we know precisely what physical or software events push our system to transition.
That brings us to Section 4, Managing Complexity with Superstates.
So think about it. If a simple kitchen microwave requires all those states and tables, how on earth do we diagram the behavior of something massive, like a commercial aircraft, without it turning into a completely unreadable mess of lines and boxes?
Well, the answer is a lifesaver called the superstate. A superstate is essentially a conceptual box on your main diagram that bundles up a bunch of related substates. It completely hides the messy internal details to prevent visual clutter on the high-level view. But when you need to see exactly what's going on, you can just zoom in and expand that superstate on a separate, detailed diagram.
Let's apply that right back to our microwave. Earlier, we saw just one single state called operation. But look here, operation is actually a superstate. When we expand it, we uncover a whole mini-system inside. It starts with a checking state to ensure everything's safe. If it's all good, it moves to cook, firing up the generator. When the timer hits 0, it jumps to done and blasts the buzzer. If a fault is detected, it triggers an alarm state. This hierarchical organization is absolutely essential for keeping complex software engineering models manageable.
Finally, Section 5, Exam Focus and Conclusion. Okay, listen up, because this is where we lock in those grades. A really common pitfall for students is mixing up data-driven and event-driven systems. Please burn this table into your memory. Data-driven modeling, that's for business systems, triggered by data availability, mapped with activity or sequence diagrams, and it focuses on end-to-end data flow. Event-driven modeling, that's your real-time control systems, triggered by events, mapped with state diagrams, focusing on finite states and transitions. Nail that contrast, and you're golden.
You've also got to have your definitions down cold. Remember, a behavioral model shows the dynamic execution of a system. Stimuli are your triggers, either data arriving or an event happening. And a superstate is your best friend for managing complexity by tucking substates into one neat box.
To wrap up today's explainer, I want you to carry this core philosophy with you. Structural models are fantastic. They give us our static blueprint. But behavioral models, they breathe actual life and movement into that architecture. They map out the timeline, the event processing, and the concrete logic that we desperately need to write functioning, dynamic program code. And that perfectly tees up a pretty massive question for our next session. We just learned how to map out all this intricate system behavior, right? Well, in model-driven engineering, models are the final product, not handwritten code. So how on earth do we feed these behavioral diagrams into a computer and have the system automatically generate the executable code for us? Think about that. It's a real game changer. Thanks so much for joining me, and I'll see you in the next explainer.